Hello everyone, welcome back. In this video we'll be taking a look at the algebraic limit theorem. So this theorem is a really useful one. It's a pretty useful theorem. So if you remember from the previous videos that when we were proving that the limit exists for a sequence, we were doing the difficult work of finding the n in terms of epsilon and all that. But the algebraic limit theorem now guarantees using this theorem we can now just uh, substitute the limit in the sequence and show that it exists, or show that the limit of the sequence is equal to that number. So it says that the limit of if so let the limit of an be equal to a and the limit of bn be equal to b, then the limit of can, where c is a real number, is just equal to ca, where a is the limit of an, remember, and the limit of an plus of the limit of two sequences added together is just equal to the limits of the individual sequence added together, and the limit of two sequences multiplied together is just equal to the limits of the two sequences multiplied together, and so is it for the division. So let's go ahead and prove this before we start using them. So the first one should be pretty easy. It says the limit of can is equal to ca, and we know that the sequence an tends to a. So since we know that an tends to a, we know that for all epsilon greater than 0, there exists an n such that for all n small n greater than n, an minus a is less than epsilon. So since we know that an converges to a, we can make this as small as we like. We can make it as small as we like. So let's see what we mean by that. But before that, we need to show for all epsilon greater than 0, there exists an n such that can minus ca is less than epsilon. That's what we need to show. We need to end up with this somehow. So can minus ca can be written as minus a. Now this an minus a looks like something we know. We know that an minus a converges to a. Since we know it converges to a, we're guaranteed that for whatever value of epsilon we choose, it will converge to a, because it means, because from the definition we know for all epsilon greater than 0, so for all values of epsilon it will converge. So we can make an minus a, the modulus of an minus a, as small as we like. We can make this distance as small as we like. So I'm going to make it such that it's an minus a is less than c, let me write that more neatly, less than c epsilon. Right. Now this modulus of c, so we know that there exists an n such that this is true, because it's true for all epsilon greater than 0. Sorry, we should have done epsilon over c, not c epsilon. It should be epsilon over c. Now can minus ca can be written as modulus of c modulus of an minus a, which in turn is less than modulus of c epsilon modulus of c. Where did I get this from? I got this from right here, which is equal to epsilon, because the c's cancel out. So we get that can minus ca is less than epsilon, because can minus ca is equal to this, and the right hand side is equal to this. So combining these two together, we get can minus ca is less than epsilon, and this looks exactly like what we wanted to show, and we're done with the proof. So Before we continue, I want to say that it is a good idea to take an inventory of what we mean to make less than epsilon, and what we're given can be make small for suitable choices of n. So for this previous proof, we wanted to make CAN minus CA less than epsilon, and we were given AN minus A is less than anything we like, because since it's guaranteed to converge to A, we can make it less than anything we like. We can make it less than C epsilon, we can make it less than epsilon over C, we can make it less than 7 epsilon, we can make it less than epsilon over 1,000. So since it's we're guaranteed, we're told that A and A converges to A, we can make it less than whatever we want. So let's go ahead and prove the second one. It says that limit of two sequences added together is the same as the limits of just two individual sequences added together, and we are told that AN converges to A and BN converges to B. So let's see what we know there exists an epsilon such that AN minus A is less than epsilon, and we can make this as small as we like, and so that is it for BN minus B. So what do we need to show? So we need to prove, so for any epsilon greater than 0, let epsilon be greater than 0, we seek n such that AN plus BN minus A plus B, remember A plus B is the limit, is less than epsilon. So we seek n such that this is true. So let's do the scratch work first. Remember, as previous, we always need to do the scratch work. So AN plus BN minus A minus B less than epsilon. I'm going to rearrange this to AN minus A plus Bn minus B being less than epsilon. And remember, from the triangle inequality, this is the same as less than or equal to An minus A plus Bn minus B from the triangle inequality. And now An minus A looks and Bn minus B soon looks like something we know, because we know An minus A converges and Bn converges to B. So we can, since we know these two converges, we know that AN converges and BN converges, we can make them as small as we like. So I'm going to make them to be less to we know we can make them as small as we like. So I'm going to make them to be smaller than epsilon over 2, and Bn minus B to be smaller than epsilon over 2. So there exists an n1, there exists an n. So since we know AN converges to A and BN converges to B, there exists for all epsilon greater than 0, there exists an n. So I'm done with the scratch work of the proof. So this is the n1 and this is n2. So we're going to choose n1 as epsilon over 2n and n2 as epsilon over 2 also. That's just a coincidence, and sometimes they might be different. So let's do the proof formally. So for all epsilon greater than 0, there exists an n1 such that for all n greater than n, I'm not going to write that right here, an minus a is less than epsilon over 2. And for all epsilon greater than 0, there exists an n2 such that for all n greater than n, bn minus b is less than epsilon over 2. So I'm going to say, so we seek this one n, we seek this n such that this is true. So I'm going to say let n equal to the maximum of n1 and n2. So let's see why I chose it to be the maximum. Let's take a look at this visually, graphically, so it makes more sense. So consider this sequence AN, which is in yellow. and this sequence bn, which does some weird things at first, and then it starts converging right here. So the for the yellow sequence, and let's look at the limits. So this is a right here. So because the yellow sequence is, for example, let the yellow sequence be an, and let the green sequence be bn, and they both start converging. So let's see why we choose the maximum. For the yellow sequence n, this is the tube right here. For the yellow sequence, n starts right here, n is smaller, and for the green sequence, n starts right here and is quite, it enters the tube after a certain time. It doesn't enter the tube when the yellow sequence enters the tube. It enters the tube, or it enters the tube when after some time. So n is larger for the green sequence. And well, what I mean by entering the tube, I mean when bn minus b is less than epsilon. So for the green sequence, so this is n2 and this is n1. And the reason we choose the maximum is that if we choose n equals to n1, which is smaller, then we're only guaranteed that the yellow sequence is in the tube. The green sequence is not in the tube when we choose n1, as n is equal to n1, because we see the terms right here, such as the ones I'm circling right here, which are not in the tube. But if we choose n as n2, we're guaranteed that both sequences are in the tube, because since n2 is the maximum and it's after n1, and since n2 is after n1, all the yellow terms are in the tube, and so are the green terms. They're all in the tube. Therefore, we choose n to be the maximum of n1 and n2. So now that we have n, the one we're looking for, we were seeking this n, so we can go ahead and prove this. So an plus bn, so I'm going to just do the scratch work in reverse, just as we did in previous videos. Minus a minus b, this can be written as an minus a plus bn minus b, and from the triangle inequality, this can be written as an minus a plus bn minus b. And since we chose and since we know both of these converge to epsilon, and they both converge, and we can make them as small as you like, and we chose n1 and n2 such that they're both less than epsilon over 2. So these are less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Since because of a clever trick of choosing epsilon over 2, now they're both equal to epsilon, and we get that this sequence as a whole is less than epsilon, and that's what we wanted to show, and we're done with the proof. So let's take a look at how to prove the third case. So we're told to prove that the limit of a and bn is equal to ab. So let epsilon be greater than 0. So I'm doing the template part of the proof. We seek n such that for all n greater than n, a and bn minus ab is less than epsilon. So let's do the scratch work first. So scratch. So we have to manipulate this sequence. We have to manipulate a and bn minus ab into something that looks like an minus a and bn minus b, because that's what we know. We know that a converges to an converges to a, and bn converges to b. So we're going to use the age-old mathematical trick of adding something and subtracting something. So an minus bn, we're going to do minus abn plus abn minus ab. So because of this clever trick, let's hope it works somehow. And so this, I'm gonna simplify this. So this is the same as bn an minus a plus a bn minus b. So, and I'm going to use triangle inequality, and we'll get that bn an minus a plus a bn minus b. This is the same as bn an minus a plus a bn minus b. So we're sort of there. We know so we've gotten something that we know that we have got an an minus a and bn minus b, which we wanted, but we've got some problems. We've got this variable term bn, and we've got this constant a. So let's see what we can do about this. So let's see what we can do about this. So we know bn is a convergent sequence, and from the previous video we know that all convergent sequences are bounded. We know bn converges to the limit b, so it's a convergent sequence, and therefore all convergent sequences are bounded, and this is just a constant, so we can handle this anyway. So we're going to choose n1 such that this is less than, we're going to say bn is bounded by m. So we're going to choose n1 such that it is equal to epsilon over 2m, and we're going to choose n2 so such that it's equal to epsilon over 2a. So we're done with the scratch work. Let's go and write this out more formally. So for all epsilon greater than 0, there exists an n1 such that for all n greater than n1, an minus a is less than epsilon over 2m. Since we know an converges to a, we can make an minus a less than or as less than whatever we want. We can make an minus a as small as we want, and so is that true for the sequence bn, because we know it converges. So there exists an n2 such that for all n greater than n2, bn minus b, we can make it as small as we want. I'm going to make it smaller than epsilon over 2a. So let n equals to the maximum of n1 and 2. So we found that n, we were seeking that n, remember? So we found that n. So let's just write this out. An bn minus a bn plus a bn minus ab. Although we did all this work in the scratch work, we need to do all of this more formally. So this is the same as bn an minus a plus a bn minus b. And from the triangle inequality, this is less than or equal to bn an minus a plus a bn minus b. And we have chosen and we know that an minus a is less than epsilon over 2, and we know bn is bounded, so this is of course less than m an minus a, because this is bounded, so bn is less than m, so we get this whole sequence as a whole is also less than this, and we know this is less than m dot epsilon over 2m. That is how we chose our an minus a to be, and this is less than epsilon over 2a, and all this cancels out, and finally we just get epsilon, because m and m cancel out, a and a cancel out. We get epsilon over 2 plus epsilon over 2, which is equal to epsilon, and we get that this sequence a and bn minus ab is less than epsilon, which is what we wanted to show, and we're done with the proof. So let's take a look at the fourth and final case. Alright, let's take a look at the fourth theorem. So we're supposed to show that an over bn is equal to the limit of an over bn is the same as the limit of a over b. So to show this, let's use the previous theorem. So an over bn can be written as an dot 1 over bn, and now we can use the previous theorem to show that to prove this theorem. Now all we need to show is that the limit of 1 over bn is equal to 1 over b, and we can use the theorem 3 now to show that an times 1 over bn is equal to a dot 1 over b, the limit of this. So let's see if we can prove that the limit of 1 over bn is equal to 1 over b. That is, the sequence 1 over bn converges to 1 over b. So let's do our scratch work as usual right here. So we have to show that 1 over bn converges to 1 over b. So we can write this as 1 over bn minus 1 over b less than epsilon. So we want to get something that looks like bn minus b, because we know bn converges to b. So this can be written as b minus bn over b bn. Right, I'm just splitting the fractions, and the numerator looks like something we know. And in the denominator, we can easily deal with the case of modulus of b, but it's more difficult to deal with the case of modulus of bn, because that's something we don't know. That's a variable term, that's a sequence. So just like as we did for the previous proof, we want to create a sort of a bound on bn. So we want to create sort of a bound on 1 over bn. So 1 over bn should be less than something. So that's the same as proving that bn is greater than 1 over something. So we have to find this. So since we know that bn converges, we can write bn minus b. We know that bn converges, so we can make it as small as we like, and we can choose whatever epsilon we want. So we can say bn minus b is less than modulus of b over 2. I'm choosing epsilon to be modulus of b over 2. And now this is the same as writing this as b over 2 minus b over 2. Well, this and this is the exact same thing. That's what modulus means, positive or negative. And this can be simplified into 3 over 2b and b over 2. I'm just adding plus b to both sides. And that's what we wanted. Here from this side we get bn is greater than modulus of b over 2. And that's what we wanted. We wanted bn to be greater than something, remember? So let's write this proof of more formally. So I'm going to say, so let's do the template part of the proof. Let epsilon be greater than 0, we seek n such that 1 over bn minus 1 over b is less than epsilon. So choose n1 such that bn minus b is less than b over 2. Now this implies that bn is greater than modulus of b over 2, which implies that 1 over bn is less than 2 over modulus of b. And choose n2. Remember that we want to somehow manipulate it to, we want to get this as the end product. So choose n2 such that b minus bn. Remember that bn minus b is exactly equal to b minus bn. If you remember, one of the absolute value proofs was y minus x, modulus of y minus x is exactly equal to modulus of x minus y. So b minus bn is exactly equal to modulus of bn minus b. So choose n2 such that modulus of b minus bn is less than epsilon b square over 2 for all n greater than n2. Let n equal to the max of n1 and n2. Now we get 1 over bn minus 1 over b to be equal to b minus bn over b bn, which is equal to modulus of b minus bn over modulus of b times modulus of bn, which is less than epsilon over b square over 2. This is from here dot 1 over b dot 2 over modulus of b, and all this cancels out and we just get it as equal to epsilon. So we have shown that 1 over bn minus 1 over b is less than epsilon. Therefore 1 over bn converges to 1 over b, and we can just use the previous theorem to show that now this is true, and we're done with the proof. So hope you guys enjoyed this video. See you next time.